So next is we have bound variable, free variable and scope of the quantifier, scope of quantifier. So when do we say that a variable is a bound variable in a given statement? So bound variable means whatever may be the statement given to us and whatever variable is represented in that statement, and if that particular variable is having any of the quantification symbol means, then it is said to be a bound variable. If not, it is said to be a free variable, right? Say, let me give you a statement as some men are clever, right? Some men are clever. Some men are clever. So we'll write what here? M of x, x is a man. C of x, x is clever. X is clever. Some men are clever, which means that some, in the sense we have the quantification as there exists M of x and C of x. M of x and C of x. Some men are clever. Now in this I'll just tell you how to find out the variable is bound or free or scope of the quantification. Alright. So now here bound variable means it says that whenever we have a statement, we'll have to look into the variable. So if that variable is quantified by any one of the quantification, then that variable is said to be a bound variable. See, look at this example. So in this example, here x is a variable and this variable is bounded or it is attached with the quantification symbol as existential. So therefore, this variable is said to be a bound variable. This variable is said to be a bound variable. Then what is all about a free variable and then the scope of the quantifier? Let me give you another example also. So for example, if we have it to be as for all x, p of x and q of y, conditional, there exists x, p of x comma y. Suppose, say for example, this is a given statement for us, and how do we identify? Here what I have said for the bound variable is that whenever in a given statement, if we have a variable and if that variable is quantified by any one of the quantification, then that variable is said to be a bound variable. So free variable is otherwise it is a free variable, which means that if it is not quantified, if the variable is there in a statement and if it is not quantified by any one of the quantification symbol, then it is said to be a free variable. Look at that here now. So how many variables are here? I do have the variables to be as 2. X and y are 2 variables I have. So now I'll have to see to that which variable is quantified. I have x, y here, but then only x is quantified with the universal quantification symbol. And again the same thing. So which means that here bound variable is x. Free variable, how do we say that the variable is free? If it is not quantified by any of the quantification symbol. So free variable here is, if you just see here, the variable y is not quantified by any of the quantification symbol. So it is said to be a free variable. And next is scope of the quantifier. So what do you mean by the scope of the quantifier? Scope of the quantifier is whenever we have a formula or any part of a formula which is followed by the quantification symbol, that is called as the scope of the quantifier. Now look at this, so we have here 2 parts. One, the scope of the quantifier here is scope of the quantifier. So what I have told you is that scope of the quantifier is if any formula is followed by the quantification symbol, then that part alone, it is called as the scope of the quantifier. Now look at this, so the entire thing you call it to be as the scope of the quantifier, or I can say that p of x comma y. So here this p of x comma y, it is a part of the formula and it is followed by this. So therefore the scope of the quantification is this. Again I can have the entire one, that is also my scope of the quantifier. So this is all what is about bound variable, free variable and the scope of the quantifier. I do repeat this, bound variable is a variable which is quantified by any one of the quantification symbol, and the variable which is said to be free is that it will not be quantified by any one of the quantification. Scope of the quantifier is that any formula or any part of the formula which is followed by any one of the quantification symbol, that part alone, leaving out that quantification symbol, that part alone, whatever formula we have it, it is called as the scope of the quantifier or quantification. So that is what here, right? So now after understanding all about bound variable, free variable and scope of the quantifier, next we have rules of inference. Sorry, this pen is not writing. Rules of inference or inference theory we have. So the same thing, whatever we have seen in the propositional logic, that is we have rule P, rule T and rule CP. So rule P is nothing else but whenever we need a premises at the point of derivation, it can be inserted at any point of time. That is called as rule P. So rule P is that is at any point of time the premises can be inserted. That is inserted. That is rule P. And rule T is we will have to apply the suitable laws of implication, that is laws of implication or equivalence. We will have to use it and then we will have to simplify it. So that is called as rule T. That is we have already seen 7 basic, very basic logical laws of implication and equivalence. So using that one can apply this rule T. And then rule CP. So rule CP, it is that if we think that if any of the premises is needed at this point of time for the derivation in order to get the conclusion part of the problem, if that is missed out, we can add a new premises. So added premises will be called as rule CP. So this is what about this. Before that also, we will say that we have rules of inference as universal generalization. Universal generalization, it is in short written to be as UG. That is generalization. Universal, we all know that the quantification symbol is for all x. Any statement we can have P of x. This is universal generalization. A statement will have in this form. And next is universal specification. Universal specification, that is US. We only have a specific form, right? Say for example, we do have it to be as P of A. Let me explain that in the further thing. That is, next is existential generalization. Existential generalization, that will be represented as EG. So that is there exists x P of x. And next is existential specification. Existential specification, ES. So we will write this to be as specifically some point P of A. So this is how we have the various notations. So universal generalization, it is UG, and this is how the statement will be. Let us see how do we get that statement. Right here. So if any statement is given, say for example, if a statement P of A, it is true for only A, right? How do we generalize this statement? How do we so P of A, it represents, say for example, I can say that Sita sings. Sita sings. So Sita, it is a subject, I represent it to be as A, and predicate is sings, so that is how. So universal generalization, everybody sings. So how do I represent this singular thing, specific thing to a generalization form? So whenever I am applying a rule called rule UG, I can write this to be as implies. So this is true only for a particular person. So which means that I have to generalize it now. So when I have to generalize, it must be true for all. Say suppose for example, if Sita is in this class, so I can say that Sita sings. So that will be applicable only to Sita. So if I have to say that all the students in this class are good at singing, so how do I generalize from a single person to all persons? So say for example, if I have 34 students in this class, all 34 are good at singing. How do I represent it from the given single point? So this I can generalize it to be as for all x, right? P of x, which means that if x is a student of this class, definitely the student sings well, which means that all the students in this class, that is all 34 students, are good at singing. So now from this single point what it says, Sita sings. If Sita is a student in this class, then she is singing, good at singing, very good, fine. So we can write it to be as P of A, right? A represents Sita, P represents singing. So now how do I generalize the same statement to the entire students of this class? Say for example, if I have 34 students in this class, I will have to represent the rule UG. How I can represent the rule UG here is that, so whoever is belonging to this class, definitely that person will sing well, right? So it is for all x, P of x. This is how we will be generalizing it. And next is universal specification, that is the rule. We have the rule as US. So from the generalization part, so suppose for example, if I have for all x, P of x, for all x, P of x, how do I write this to be as universal specification? So now the same example we can take it, that is all the 34 students in this class are good at singing. So now I will have to say that only one student is good at singing from this point by using the rule universal specification. How do I denote that? That is, specifically if I want to point out only Sita is good at singing in this class, so I can write this will imply P of A. What is this? A represents Sita and P represents singing. So Sita is good at singing. If I make use of the rule as US, definitely I will be able to get that. So in a similar manner, existential generalization, how do I get this? Suppose for example, if I have got P of A alone, say, right? So P of A alone, so which means that again the same example we can take. So this is what EG, that is universal generalization. So I have the statement as only P of A. What does this P of A represent? I said that Sita sings or Sita is good at singing. So this is P of A. Now that I will have to generalize this using the existential quantification. So which means that I can write or I can represent this to be as there exists x P of x. So what does it represent? There exists x is nothing else but one student of this class is good at singing, fine. So now one student, who is that one student? Sita is one student who belongs to this class. So therefore, I can represent that to be as there exists x P of x. So there exists x, that is existential quantification, means it is applicable either to one person or a few person or some person of that class. I mean the same thing here. And next is existential specification. So that is rule ES. How do I get that rule ES? Let us see. So say for example, some students in this class sing well, right? Are good at studies, whatever the predicate term you take it. So now I will have to specifically say that, or point blank I will have to say that only 1% is capable of doing that. So if I have to say that only one person is capable of doing that particular thing, that is if Sita is a student, then she sings alone. So which means that I will have to write this to be as P of A. What does it mean? So, P of A means that from here, this entire, that is there exists X, P of X, what does it represent? One of the students. So, I have said that there are 34 students in this class. Among the 34 students, Sita is also one among them. So, therefore, I will be able to say that one student sings well. So, therefore, I can write it to be as what? P of A. So, that is all about this. Now, after understanding what is the rules of inference under the predicate logic, we will again make use of these inference rules into the problems, and then we will be able to get either the direct proof or the indirect proof. Again, I will be recalling the direct and indirect proof. So, what is all about the direct proof we have? So, we will be given with n number of premises, and also the conclusion will be given. So, we will be in case of a direct proof, what are all the steps we will be following it? The first step will be it should end up with the finite number of steps. That is the conclusion part we must be able to get with the finite number of steps. And the second point is that whenever any premises is needed at the time of derivation, it can be inserted. And then we will be applying the rules of logical laws of implication and equivalence, and finally we will be able to get the conclusion at the last point. And what is all about indirect proof? So, indirect proof, the first thing, the first and foremost thing is that we will have the negation of the conclusion as one of the premises, and then the same steps will be followed as that we have done for the direct proof. And the final, instead of the conclusion, since because already we have taken the negation of the conclusion as one of the premises, the last step instead of that, what we should have is that we should have it to be as a contradiction. That is, the last step should be false. So, unless otherwise the method is not mentioned in the problem, either way we can use it. Either we can make use of direct proof or we can make use of the indirect proof. So, specifically if the question has been asked to use direct proof and get it, we will have to make use of only the direct proof, or if it is used by indirect proof, definitely we will have to make use of only the indirect proof, and then we will have to get the conclusion part. So, now let us see the problems. We will have to check the validity of this statement. So, as what we have discussed earlier in case of the propositional calculus, here also we will have to identify the keywords and assign the predicate terms to the identified keywords, frame the premises, and then we should be able to get the conclusion either by the direct proof or by the indirect proof. So, now let us see what are all this here. We have lions, right? So, L of X, X is a lion, X is a lion. Then definitely it is a dangerous animal. So, D of X, X is a dangerous animal. So, these are the two keywords we have identified in the statement. Now, with that we will have to frame the premises. Lions are dangerous animals. What is meant by lions are dangerous animals? If it is a lion, definitely it is a dangerous animal. And now here in the statement, nothing is said about the quantification. Either we will have to make use of universal quantification or we will have to make use of existential. That is not specifically point blankly it is given here. It is not given. So, we will have to. So, whether the lions are dangerous or not? Yes. Of course, all lions are only dangerous animals. So, which means that we will have the quantification to be as for all X. If it is a lion, definitely then it will be a dangerous animal. Fine. So, lions are dangerous animals. Here we have. Then, there are lions, which means that you can take the universe of discourse to be animals, right? The animals, not necessarily that it is only lion. We may have lion, we may have tiger, we may have elephant. So, likewise we will have the universe of discourse, and in this problem what we say is, we talk only about the lions. There are lions, which means that among the universe of discourse we also have lion. So, what quantification I will have? Lion in the sense I will write it to be as L of X. What will be the quantification for representing this lion alone? There are many animals, right, in the universe of discourse, but one of that is lion. So, therefore, we will have it to be as there exists X. Therefore, therefore in the sense it implies there are dangerous animals. Definitely, we have the animals which is dangerous and which are all also not dangerous. So therefore there are dangerous animals. So D of x D of x, dangerous animals. Now I'll have to see to that whether I have I should make use of the quantification symbol as for all or existential. So which is more appropriate, I'll have to find it. So the universe of discourse, what I've said, it is all animals. Animals in the sense I can have cat, I can have dog and so on also. So it doesn't mean that all the animals in the universe of discourse are lying. Only few are dangerous. So which means that some are dangerous, they exist. Understood now how to frame the premises? So we have identified the keywords, we have indicated the predicate term of the identified keywords and also framed the premises, and then we will have to derive. So our intention is to get this. Let us go by the direct proof. So we have serial number, we have the statement, then we have the explanation part. So now the first thing is that we will take any of the premises, not necessarily that we have to go only in a sequential manner and then take it. Any premises, if you want it, we can take it. So let me say, for example, I will take this, that is there exists x L of x. So what the thing I have done here, I have just inserted the premises here for my derivation. So therefore the explanation should be what? Rule P. Now if I want to make use of laws of implication or equivalence, I will have to remove this quantification symbol. Only if I remove it, I can apply that. So therefore, so if I want to remove this, what is the suitable law? We know that. So here I have a existential generalization. I will have to point blankly say that only this is true for this case. So therefore I can apply ES. So ES on 1, what do I get? I get it to be as whenever I convert it, so this x has to be point blankly mentioned to only one particular thing, right? Either one subject or object I should have. So therefore I can have it to be as L of A. Understood? This is a very, very important point one have to keep in mind. Whenever I am in a position to apply the logical laws of implication or equivalence, I should have to remove this existential quantification or even the other quantifier. If I have to, I'll have to remove it. So in order to remove it, I'll have to make use of this ES, that is point blankly I am telling existential specification. So this will go off, and when this goes off, the variable has to be changed to a specific thing. Let me take it to be as L of A. So next is we will have for all x L of x conditional D of x, right? So this is rule P. And next is, look at this. Now again we'll have to remove this for all x, and I'll have to, for all is what? Universal. And now I have to point blankly denote this is true only for this particular case, that is US on 3. So I'll have L of A conditional D of A. Whenever I am removing this, x has to be replaced to be only by a specific term. So now see here 2 and 4, for 2 and 4, if I apply detachment, right? Detachment on 2 and 4. On 2 and 4, unless otherwise you are thorough with those laws of implication and equivalence, we cannot do anything. So you should be very thorough. So detachment is what? What does that detachment say? I'll write here. P comma P conditional Q will imply what? Q, law of detachment. So P is this, P conditional Q is this. So we will be able to get what? D of A. Fine. So look at the conclusion part. I have there exist. So I'll have to attach this. So if I have to attach it is what kind of a quantification? It is existential. So I have to generalize it. Fine. EG on 5. So we'll get it to be as there exists x, and this has to be changed. So it should be generalized. So this is how we'll have to do it. So now we have proved it by the direct proof. Now understood this? Okay, again we will do a few more problems. All integers are rational numbers. All integers are rational numbers. Some integers are powers of 2. Therefore some rational numbers are powers of 2. So now we'll have to check the validity of this statement. All integers are rational number. All integers are rational numbers, which means that first of all I'll have to identify the keywords. So when I have to identify the keywords, all integers, right? I of x represent x is an integer. Fine, good. X is an integer. I have integer, I have rational numbers, I have powers of 2. So these are the 3 words we have identified in this, and we will have to accordingly assign the predicate term, right? Rational numbers. So R of x is a rational number. X is a rational number. Then power of 2 also we have. P of x is power of 2. Okay, powers of 2 or power of 2, whatever may be the term, we write it. So now these are the identified keywords and we have assigned the predicate terms. Now let us see. All integers are rational numbers. All integers, definitely if it is an integer, it is a rational number. That is what it means. So all na we will have for all x. All integers is I of x. If it is an integer, then they are rational numbers. So if and then we have the conditional connective. So first premises is over. And next is some integers are powers of 2. Some integers are powers of 2. I will have to connect these two. So some na I will have there exist x. Some integers are powers of 2. So powers of 2 I will have it as and here and P of x. Then therefore this should imply some rational numbers. Some in the sense we will have existential quantification. Some rational numbers are powers of 2. Some rational numbers R of x and P of x, right? So powers of 2. Now look at this. We have serial number, statement, and then the explanation, right? So again and again I am repeating that everyone will should be very thorough with the laws of implication and equivalence. So first thing, this is the conclusion. We will go by direct proof. We will take the first premises as it is. So for all x, I of x conditional R of x. So that is rule P, since because I am inserting the premises here. And now that I have said already, whenever we apply the laws of implication or equivalence, we should not have this universal or existential quantification. It has to be removed out. So if I have to remove this, it is universal specification on 1. So if I am removing this, I will have to represent it to be as I of a conditional R of a. So then again this is, I can go for what the next statement is there. So there exists x, I of x and P of x. So that is again rule P. Then the fourth one, I will have to remove this also. So in order to remove this, here I have the existential quantification. So from the generalized form, I will have to specifically say it is true. So ES on 3. So ES on 3, we have it to be as I of a and P of a. I of a and P of a. So we will have conjunctive simplification. If I use conjunctive simplification on 4, conjunctive simplification on 4, we have I of a and P of a. This is conjunctive simplification on 4, we have this. Now look at this, the final expression should be, conclusion must be connecting R and P. So now we have 2 and 5. So 2 and 5, again detachment law, see here P comma P conditional Q. So that implies Q. So we have here to be as what? Detachment law, I can apply it and I will be getting it as R of a. That is detachment on 2 and 5. 2 and 5. Again here you look at the conclusion, it involves rational numbers and powers of 2. So conjunction of these two. So conjunction of these two, we have it as R of a and P of a. So conjunction of 6 and 7. conjunction of 6 and 7 we do have this. And now see to the conclusion part, it is with the existential quantifier. So that is there exists x r of x, we will have to convert the variable in p of x. So here it is EG on 8. Now understood this? Yes, thank you.